In the last episode, we have discussed how AI can revolutionize quantum computing and redefine quantum algorithms in a much more efficient way. Maybe we have never thought about it before. And I have given an example about how AI could develop a new quantum entanglement swapping protocol, which the original researchers didn't think of. In this episode, we are gonna discuss how AI can help advancing computational chemistry, in particular quantum chemistry and quantum computing, in order to perform much more efficient quantum chemistry and the quantum dynamics simulations. So the typical workflow in chemistry or in computational chemistry in general is you have a molecular structure, and this structure, you describe it with a mathematical formalism or a mathematical equation called the Hamiltonian. The Hamiltonian is just an equation that can describe the interactions between atoms, but also the kinetic part of the energy and the relation between the kinetic part and the potential part. Typically, to calculate the quantize the energy eigenvalues or the energy state levels of a molecular system, like for example water or carbon dioxide, we use a typical workflow called variational principle. And in that sense, you try to have your Hamiltonian. That Hamiltonian, you have derived it, you did the theory part, and that have been already translated into a computational model. And then you assume a trial wave function. The wave function is just a state function or a mathematical description for a particular state where the quantum system can exist in. The wave function is quite interesting because it's a complex function, so it has an imaginary part and real part. And there was an idea about why the state function should have an imaginary part. This was also a mysterious question until a recent paper has came in where they have highlighted how and why the wave function should include both imaginary and real part. And it's like the quantum state is actually a living thing in a 2D space. Anyway, so you have the trial wave function and you try to act with the Hamiltonian on this trial wave function, and then the result will be the ground state eigenvalue. Of course, the state function should be normalized, so every time you need to do the renormalization in order to make sure that you are really describing a real quantum system or a real physical particle. But then the idea, you get this energy and then you need to update the parameters that describe the state function until you arrive to the lowest value. And this lowest value of energy will be the upper bound on the ground state energy or equals to the ground state energy that you are aiming for. In a similar manner, you can do this for all higher excited states as well. When it comes to quantum computing, we need to understand a fundamental difference between quantum computing and the classical computing, in the sense that the quantum computer is just only a way to compute with quantum mechanical systems. In that sense, the fundamental unit of computations in quantum computer, which is the qubit, the qubit itself is like a classical bit. It could be exist in 0 or 1. So in the default situation, or if we leave it without touching it, like roaming in the universe, it will be in the default state. So it will be in the 0 state. However, that qubit has a phenomenal power. It has the ability to transform and become in a superposition of two states. When you perform a specific operation on it, it will jump into this superposition state. So it can, for example, be partly in 0 and partly in 1 states, which is on the contrary to the classical bit. Hence, we come to the fundamental difference. The way that we load information in the qubits is completely, or in a major part of it, is different from the way that the information already loaded into classical bits. So into qubits, you need to encode information in a sense that it has to be stored in the quantum state that represents a single qubit or a certain configuration of multi-qubit system. Then when we do computations with quantum, since it's a quantum system, so qubits will have a particular Hamiltonian, a particular mathematical formalism that describes this configuration of qubits and how they interact with one another. And this Hamiltonian will be called a qubit Hamiltonian. Typically, since the chemistry and the physics are also sort of physics, and this is the way that's naturally computations from physics and the chemistry could be mapped into quantum computers, then it's just a matter of defining the Hamiltonian for the chemistry or the molecular structure problem, do the theoretical work and do the computational work and have it, and then map this Hamiltonian from chemistry or physics problem into the qubit Hamiltonian, into the way that qubits can think of. And in this mapping, for example, it could be done like Jordan-Wegener mapper or parity mapper, and there are several workflows that could be leveraged and used. You only need to translate the formalism of the Hamiltonian from one side to another. And what the qubits understand is actually how to manipulate them, and this is done with quantum gates. So you need to end in your transformation at the end from having the sort of the differential equation shape into Pauli gates or gate shape, where you can have gates that can act on the qubits, manipulate them, create entanglement between them, and even do the measurements to them. So that's our final translation. So if we would like to calculate the ground state energy, how we can do this on a quantum computer, there is a famous quantum algorithm. It's called Variational Quantum Eigensolver. It's like the quantum version of the variational principle. And in that algorithm, we assume that once you could transform or translate your chemistry Hamiltonian, the one for a molecular structure that you have, like for water or for carbon dioxide, you can translate it to the qubit Hamiltonian and end up in Pauli strings or Pauli gates. Then that will be what we call the ansatz, the quantum gate equivalent of your Hamiltonian. Then you need to create the trial wave function, and the trial wave function, this function will be sort of depicted as some gates with some coefficients that will act on the qubit state or the multi-qubit system state. And that parameterize the gates could be like rotational gates with certain of angles. If you vary those angles, then every time you end up with a state that could be potentially the ground state or the eigen function state of the Hamiltonian. However, you don't know that. You need to change those parameters like the theta and the phi and play with them, and every time you change that, you act with your Hamiltonian. And then you execute the quantum circuit, and then you measure, and then you calculate the expectation value, and then you check that the value that I get is the lowest one or not, and then you feed again that value to the classical computer, and the classical computer will do updates for these parameters that you are using in your trial wave functions or these trial gates that you are using to represent the coefficients that you wanted to change. And then you do again, and then the wave function or the trial wave function will change, and you act on it then with the Hamiltonian. And then you execute, and then you do the measurement. And you see, this is why the Variational Quantum Eigensolver is a hybrid quantum classical algorithm, because it works hand in hand between, it is a collaborative work between a quantum computer and the classical computer. You keep these iterations until you find the lowest energy that's possible for the system, and this will be your ground state. If you have a small configuration space, one parameter or two in your trial wave function could be enough. However, sometimes you might end up with hundreds of parameters in order to have the good trial wave function. And the good one will be the eigen function of this particular Hamiltonian and will represent the ground state. In that sense, there's a lot of algorithms that try to optimize, and it optimizes the values that you obtain and check, are you going higher or lower with respect to tiny changes that happens on those parameters that you are using in those angles. Like you can increase them, you can lower them, you can increase part of them, lower part of them, and so on. And some algorithms like the gradient descent are already used and deployed in order to optimize this situation. But what if you have too many parameters in your system? Here it comes the bottleneck that this is very complicated and might be computationally expensive, and you might need very long time in order to converge your parameter space and achieve the correct trial wave function, and consequently calculate the ground state energy. For that sense, AI can help. In a recent paper published by researchers from several institutes and the companies around the world, including NVIDIA, they have published very good paper that leverages the Generative Pre-trained Transformer based architecture to optimize the workflow of Variational Quantum Eigensolver. And in this particular workflow, instead of having this big amount of parameters that you need to optimize in order to obtain the good trial wave function, this GPT QE, or the Generative Pre-trained Transformer based Eigensolver, can help you deduce the correct or approximate the correct segment of parameters from the subspace of parameters that will achieve for you the good results. And it works by sampling over the measurement and optimize the workflow in a sense that you don't need too many iterations. You are just sort of work on a pre-information that you obtain from every iteration in order to optimize the calculations that you are doing with VQE. Of course, this work is revolutionary because in that sense, instead of keep the iterations in a way that might take very long time, you are sort of not blind, and you have sort of like guess every time using the information that you obtain about what could be the good set of parameters, and use that in order to shrink or reduce the number of iterations significantly to obtain the ground state energy. So in this workflow, the constructed circuit or the constructed ansatz is sort of efficient and can help in achieving the required result very fast. I'm gonna leave the link of this paper below. Feel free if you have any question to ask. And the beauty about this paper, it's not only applicable to chemistry, but also it can be extended to any optimization problem that require finding the ground state energy of a Hamiltonian using VQE. For example, like in finance, in portfolio optimization, risk assessment, all of these problems, including quantum machine learning and reinforcement learning, are about how to map this problem to a minimization problem. So you need to end up with a minimization, which you can map it to a particular Hamiltonian, and that Hamiltonian can be mapped to the qubit Hamiltonian, where you need to find the ground state energy. So the ground state energy, which is the minimal energy for this particular Hamiltonian, it is sort of the equivalent for the minimum values that you are looking for in portfolio optimization or logistics optimization or any kind of these applications. Because after all, we are dealing with qubits, and qubits are physical systems that understand the language of Hamiltonian. Hamiltonians only describes how these qubits are interacting and how they are coupled and how they are talking to one another. Feel free if you have any question to send it to me, and until next episode, see you.